All right, well, so Justin, thanks for the introduction, and hi to everyone. It's first time joining the community, so I appreciate that. I appreciate the chance to share some of my experiences and get to know all of you guys. Justin gave an intro, but just by way of a little background, in my current role, I lead the functional teams at the Advanced Analytics Center of Excellence at Ecolab. In practical terms, means I'm responsible for the data science technology platforms and standards. So what tools, languages, best practices do we want to adopt? More recently, I work a lot on the question of how our teams can smooth the transition from proof of concept models to machine learning enabled products in the real world. As part of that, the offshore teams, so we have a team in India, two teams in India actually, that report into me. So we try to find ways to collaborate together to build products. A little bit about the evening. So how did I kind of lay this out? There's a lot of buzz in the machine learning community on the topic of MLOps. So I thought we would start by defining why there's such an interest in the area. What is MLOps, why we need it? Once we nail that down, maybe dig into how data science is evolving in organizations. Because MLOps it is about the technology, but it's also about how you collaborate with others to build products. So we want to shift the focus a little away from the model to the product that ultimately is going to be consuming that model. And then we'll talk about tools and best practices to enable teams to hopefully more successfully operationalize their work. I'm not going to do a demo tonight, but maybe that'd be something for another discussion or for another day. So if we want to understand why there's such an interest in MLOps, you could probably sum it up with this one tweet. This was issued in 2018 by the then Senior Vice President of Conferences at O'Reilly Media. And it pretty much sums up the problem with, or the problem that organizations are having when it comes to machine learning. If you work in the space, it may make you guys laugh. It kind of made me chuckle the first time I saw it. But it's only funny because I think it's a challenge that we all face. So if you break it down a little bit, what's she really saying here? Given a clean, static data set and a clearly defined problem, not to say that's easy to come by, but given those things, and if you assume that there's a reasonable relationship between the candidate features and your outcome variable, you can probably build a machine learning model in a pretty short period of time. That's not saying that it's the best model or it's a sophisticated model or it's even a good model, but you can probably build one. But once you get that completed, the question of what comes next is what surfaces. And the challenges that you have to really overcome to migrate that trained model into a production environment, both can be and are significant in most organizations. And in many cases, you really can't get past that at all. So you ask yourself, well, why is this so hard? There was a paper published in 2015 at the NIPS conference, and researchers there, they discussed the hidden technical debt in machine learning systems. They state while machine learning offers the potential to unlock tremendous value, there are also massive challenges to deploying and maintaining production-grade products that utilize machine learning. Notice the emphasis here is on products, not on models. Fundamentally, the challenge here is that any product that contains a machine learning model is an ecosystem, and that ecosystem by design interacts with and changes the real world. Those changes get reflected in new data that the model receives, and then you create a feedback loop between the model and the real world that you have to manage over time. Otherwise, the model's performance degrades, and eventually you stop delivering on the expected value. So fast forward a few years, and what's happening? Organizations everywhere report that most machine learning initiatives fail. Doesn't matter if you're talking to Gartner, MIT Technology Review, whole companies have popped up trying to help solve this challenge. It's just really, really hard. So if hidden technical debt is the challenge, then we need to take a look and try to understand what technical debt is and what we can do about it. So technical debt it's a metaphor to help us reason about the long-term costs associated with moving quickly in software engineering. The reality is when we move quickly, we might deliberately choose not to implement a best practice. We might bypass a standard, and we might do those for very solid, sound business reasons. We have to meet requirements, meet deadlines. We make those choices. We have to acknowledge, though, that debt exists, and we have to service it, not with the intent of adding functionality, but in order to enable future improvements, reduce errors, improve the execution of our code, or just simply make it easier to maintain. It's like deciding not to change the oil in your car right at 3,000 or 5,000 miles. You can probably go past that, but you better change it eventually, because if you don't, it's going to catch up to you. So if we understand technical debt, we can further subdivide that into known and hidden technical debt. Known technical debt being those decisions that we make consciously and deliberately, like missing doc strings, no unit tests, or slow running segments of our code. Hidden technical debt is very dangerous, though, because we don't have the ability to assess the business risk we assume during development. Simply put, we don't know what could cause our product to fail. Any of this sound familiar? We've written our machine learning model in a mixture of R, Python, Scala, and SAS to do feature engineering and/or model building. Is our code checked into source control? How about the model that was saved, right? Did we save that into source control? What about the data that we used to train the model? That's part of the system, and it's going to impact the outcome. If you want to reproduce it, you better have that versioned as well. What about serialization? Did we pickle our model if it's in Python? If so, have we also provided all the information that we need to reproduce the environment that it was saved in, or that it was created in? All of those things lead to what the researchers call changing anything changes everything. They call it the case principle. And that's pretty much, that's one of the core components of our challenge. So all of those things have led to this convergence of a number of fields, XOps for machine learning and artificial intelligence. X being data ops. So, and these things tend to get conflated, so we're just going to define them concretely. Data ops is a term that popped up, I think it was 2014. It was introduced by IBM. The idea of providing business-ready data, quickly available for use. Is it curated? Is it schematized? Is it ready for consumption? A lot of organizations are still working on that piece of it. After that, you have the topic that we're discussing tonight, which is MLOps. MLOps is intended to help organizations and business leaders create long-term value and reduce risk when we incorporate machine learning models into database products or data-containing products. There's also model ops. Model ops is a generalized form of MLOps. A lot of organizations may have rules engines or optimizers running. You can apply these same principles there in many instances. And there are actually open source Python packages, and there's a lot of Java packages as well for rules engines. And finally, AI ops. AI ops sounds like it should be an advanced form of MLOps, but it's really not. It's really the kind of the process of solving operational challenges through using AI. So all different subsets of XOps that we may encounter. So if we acknowledge that we understand that MLOps or getting machine learning models into production is a challenge, then we have to, in part of assessing the why, it's not just about the tools, it's about how teams work. What are the contributing factors that drive this, both the generation of hidden technical debt and ultimately the complexities in getting a model into production? A lot of times it's really not about execution. It's not about building a model, but it's about how products get created within an organization. And the creation of products is in part a technical endeavor, but it's also a business process. And even more so, it's an activity of teams. It's not something that occurs at the individual level. You have to be able to work together. And if you look at our list, challenges like undeclared consumers and complex glue code, you're going to hand information, data, and other assets and objects off between team members. How do we enhance this collaboration and communication with the data science functions? So there are really three ways that data science starts to take shape and mature within an organization. So we're going to take a look at the first one. This is what I call emergent data science. And we're going to look at this through the lens of portfolio management. Portfolio management being that process of how all of the work within an organization gets prioritized and resourced. So what happens? Oftentimes you may have a handful of data scientists in the organization. Maybe those data scientists are subject matter experts, so they're budding data scientists. But they have an idea, they have a hypothesis they want to test. They get together, they go on a hunt for data. They manage to find what they need, or they generate it, they clean it, they schematize it, and then they start the activities that we call data science. They denormalize, they go through feature engineering. They go through this process, they get to a model that looks pretty doggone good, and they're pretty happy with themselves. So then they go, what next? They're using Python or R, it's kind of all over the place. But then they look around and they say, well, what do I do with it? And you have all of these other stakeholders and functions and capabilities that you have to engage. And this is just a tiny subset, because that model is not a standalone product. It has to be integrated into some other system. And their work has not been prioritized within the broader portfolio. All of these other functions, they have responsibilities they have to deal with. They're trying to drum up support. They hit a wall usually eventually. Maybe even people are interested, but it's just not a priority. So then the fallback position becomes this: I'm going to make a better model. And you get in this iterative loop, and the customer never actually gets to see all of the value that you might have been able to create, because it's not been prioritized. So from a project portfolio perspective, you've got technical feasibility, but all these other things that actually have to happen to get resourcing, they don't occur. So then the work usually dies. So as organizations get more mature in this space, so do the organizational processes mature. So then you end up with this external activity. Maybe data science is a research function. What we do is we get a cohesive team. We identify a problem. We get some business experts and domain experts. We assign a product owner. We realize that we need to find data. We engage the data engineering team with our hypothesis, and we get our data scientists together, and we start our process. We recognize it's going to be messy. We acknowledge from the get-go that they're probably going to use languages and tools that most of the organization doesn't use. Okay, so we enter this loop. We clean and we schematize our data. We do feature engineering, selection, feature selection, model training, and we get to a model. And we stay in this loop. We may stay in this loop for a long time, seeking to build the best possible model we can build. And once we complete that, we decide, all right, now we've organized. We bring all of our other resources into play. We prioritize the work, and we hand the model off to be rewritten in the language that the maintainers are going to use. Might be Java, might be C#, and we deploy. And in this process, we realize business value. There is no doubt about it. It gets to the customer. What's the gap though? The gap is this is a one-way process. If your customer doesn't realize the full value, maybe they want to see changes, there's no way to go backwards into this loop, because you've got a gap between what was done on the development side and what was pushed into production. oftentimes this gap that exists between what's in the loop and what happens outside the loop goes so far as to break the link between the data that was used to train or retrain the model and the model that's running in production. So because of that, you don't have the opportunity to iterate. In a maybe a better looking phenomena or process, you might take that customer and put them in the middle of the loop. So you iterate with them while you're in the loop, but you still lack the ability to go back out and iterate on the original work. So then maintaining this in production becomes problematic because we know the model is going to drift. We know the data is going to drift. We know it's going to need to be retrained, and there's no viable process to do this short of a massive redevelopment effort. So we take a look at it from a portfolio perspective. We can say, well, we've checked the first 4 boxes, but then at the execution level, we start running into problems, right? We've broken the link between what was done in development and our data. What's our runtime environment going to be? Are we going to run if we train the model in R, are we going to run it on our server, or are we going to rewrite it to C#? Are we going to hard code? If it's a linear model, are we going to hard code the coefficients? Right? We have very long timelines because of this rewrite and deploy and the inability to loop back into the process. That slows our process of iteration down. The data science teams oftentimes don't have line of sight to the model's performance over time. There are just a lot of question marks and gaps in this process, which contributes to the long lead times.
Hey, Greg, I just got a quick question.
Yep.
As you're talking through this, my own question do you think there's a function of just size of the organization with regards to how many issues come up, or is this going to happen even if you have a small team in your experience?
Well, I think it's going to happen even if you have a small team. And the reason for that is in any organization, eventually people are going to move on and leave, and right, those things are going to occur. You're going to get promoted. In that first process as an emergent activity, or even data science, as a research function, if only 1 or 2 people know how that model works, then just by virtue of kind of the ongoing process in teams, right?
Sure.
I get promoted now, maybe I step away from that model for a couple of years. Nobody knows what's happened with it. Nobody knows where it's saved. Nobody knows how to maintain it. It starts to collapse under its own weight.
Sure.
Yeah. Now there certainly is a scaling function.
Right. But you're right. There's always that handoff that's going to need to happen. One person isn't going to be sitting in all those seats. And so, like you said, it's kind of like the scenario of you get hit by a bus or you win the lottery, whatever it is, people move on. And then a new person comes in and they need to sort of pick up where other things were left off.
Yeah. And, if you have a scenario where, you have 6 different languages being used for data science in the organization, you hire the 7th person. Do they know, right? Do they know the language that was used in the other models?
Right.
It just becomes challenging.
Sure. Cool. Thanks.
Hey, Greg, there's a question in the chat.
Sure.
I'll read it. So it says, Kailash is saying, I completely understand the value of MLOps, but currently without MLOps, I'm still able to deploy the model either as a real-time service using Flask API or any other serving platform. If it's a batch prediction, I'm still able to productionalize it using Spark. So can you comment on that?
So the short answer is yes, I can. I will say this: the challenge is not deploying a model. So Flask is kind of an interesting side note because Flask is actually not intended for production use, but I know a lot of people use it that way. But I guess my comment there is building a model and deploying a model isn't really that hard. Building it in an organization, so that it's incorporated in part of in a product and that it is maintainable over time is the challenge. So if you think about things like traceability, there are many places now, many governments around the world are legislating that you have to have a model that's traceable to the data set that was used to train it. There's also legislation around explainability. So, because just building a model in isolation as a single data scientist isn't really the hard part. Even like I said, standing up a Flask API isn't hard, but making that model part of an ecosystem is the challenge. And it's the reason that, 80 to 90% of data science projects never actually make their way into production. So let's talk about maybe how data science is starting to evolve, the activity of MLOps. And this is not my, you can go anywhere and find this, but let's walk through what we're trying to actually, what we're trying to drive with this sort of a process. So rather than having a one-way loop, what we want to do is we want to form a team and we want to get all of our stakeholders involved in the process throughout the development lifecycle. So the basic premise is you want to make machine learning part of an agile process, but not with the intent of doing machine learning in agile, but with the intent of doing product development in agile, with machine learning teams being part of that. So the basic idea is you embed your data science teams into the product development process. So we bring a product owner in, we have data engineering, security, network finance, all of our functions, they know where they fit in the process. And when the team decides they want to incorporate a machine learning model, they go through this hypothesis generation, feature engineering, right? They may scale up or scale out, quickly build a model to deploy and run. So oftentimes data scientists and data science teams get caught in the loop of iterating on the model to build the very best model they can, and then they deploy it. In this process, we say we want to deploy something, might not be the very best model, but it's one that gets us what we need and gets us started, deploy it and put it into production, monitor and retrain. And if we have value, go back out through this loop and iterate. So can we add value by building a better model, by incorporating more features, right? Go through this iteration process, check our data integrity, go back into the loop. So if we think about how software engineering occurs in the real world today, this more mimics that process, right? We want to do incremental updates to add value. You don't do the massive releases that software engineering teams did in the late 80s, early 90s. So these get, more or less broken up into explore and prototype, develop, run and maintain type activities. And in the idealized state, we adopted a design thinking mindset and we put the customer at the center of the process. So we have a model or we have an insight that we think we can deliver through data science. Let's test it. And once we get that into production, then let's do a canary test, right? Let's run both versions side by side and watch what the effect is. And then slowly phase the old one out if it delivers the value we expect. From a portfolio management perspective, again, do we address the project risk, right? So these are all of the things that we were talking about before. We check a lot of the boxes. We can iterate. We have observability to the model because the data science teams are part of the process. Here's the challenge. Oftentimes we don't think about trying to get our data scientists to write production grade code. You say, well, we'll let them do their thing and then we'll take it and we'll give it to the software engineers. And that's the question. How do we close that gap? So the Continuous Delivery Foundation in September, they formed a special interest group with the intention of identifying best practices and reference architectures to try and address some of these concerns. They have several high-level goals. We'll go through some of them. So they first aspire to create an MLOps definition and roadmap. They want to identify reference architectures and design patterns. They want to define AI governance and risk management best practices. They assert a few things too. They say that MLOps best practices should be agnostic with respect to languages, frameworks, and platforms. So basically what they're saying is MLOps best practices should apply whether you're writing in Python or R or SAS, right? Any framework, doesn't matter where you run it. They also say, interestingly, that models should expect to be trained and executed on a variety of hardware, but you cannot assume that that model will run on the same hardware that it was trained on. So think about the implications of that for, say, Python. If you train a model in Python and you pickle that file, how difficult would it be to unpickle that file and run it on a watch in Python? Pretty challenging. But that is a reality. That's a real scenario in which a model could be deployed. They go on, they say they want to figure out how to treat ML assets as first-class citizens in DevOps processes and managing them in an MLOps workflow. They want to provide mechanisms to version training, testing, and validation sets, apply testing frameworks to your code, and then managing data security. So in their document, they call out specifically, they say notebooks, Jupyter notebooks, but other notebooks in general, are specifically called out as a risk, an anti-pattern, according to the NIPS 2015 NIPS paper, to MLOps. And that's something that makes a lot of data scientists cringe, anti-pattern. I can't use my Jupyter notebook. So why would they say that? And this sounds controversial, and I'm going to be clear. I'm a fan of Jupyter notebooks. I use Jupyter notebooks. You really can't beat a Jupyter notebook for exploratory analysis. But think about it through the lens of reproducibility. I've tried collaborating with friends and coworkers on Jupyter notebooks, and I take a notebook and I check it into source control, and then another person comes along, they check it out. They may run it a few times, make a few changes, and they go to check it back in, and they get a merge conflict. And when you start digging into the source of that merge conflict, you find out that there's a lot of hidden JSON in the Jupyter notebook. And in reality, the Jupyter notebook contains not just the code that you run, but it also contains the output of that code. And that becomes an anti-pattern for source control, because your code should be immutable, and it should be idempotent, meaning you should be able to run the same code time after time, right, in any order, and you should get the same result from a function perspective. And notebooks do not meet that criteria. So all of these behaviors represent a divergence from the whole intention of source control. And this gets back to the point that, the question that was asked earlier. Yeah, I can take a model, I can train a model, I can deploy it to an endpoint through a Flask API. I can do batch scoring with Spark or Dask or Jupyter, take your pick, right? But can I do it in a way that is reproducible? Can I assure the integrity of my code? Can I assure the reproducibility of my code? Can I give it to someone else and have them execute it without any questions about how to proceed, right? Those are where the challenges come into play. And in production systems and production environments, those are the gaps.
Can we still use the Airflow or any kind of orchestration tools and achieve that gap, right?
I'm sorry, can you speak up? I couldn't quite hear you.
No. say for example, we can use any kind of orchestration tools like Airflow specifically we use in our organization for orchestrating the pipeline in the sense, okay, extract your data, run your model, pickle your file, and then put it in production using a batch API or using the Flask API or any type of batch mode, right? So we specifically use Airflow, but that's where I was a little bit finding difficulties how different that process is from the MLOps. Is it same?
I'm going to apologize. I'm hearing about every fourth or fifth word, I think.
If you type it in, I'll ask it
Oh, okay.
for you.
Are you able to hear me now?
Yeah.
Perfect.
Yeah.
Perfect.
Okay, fine. See, currently in my organization, we use Airflow orchestration tool.
Yep.
So what it does is the feature extraction from the engineering side to model development and pickling the file and deploying as a API. So this is done using a orchestration, Airflow orchestration. So the question is more on how it is different from the MLOps, or is it the MLOps?
So I'll give me just a minute because I actually talk about some of the tools. I think that it's probably close. I think you would have to assess that yourself, but Airflow is actually a tool that is used in the MLOps process. But I might get to some of that question later on because there's a development perspective to this, and there's also a GitOps perspective. And I try to touch on both of those in just a few slides.
Cool.
Okay.
Hey, Greg, what brought to my mind was the idea of Docker.
Yep.
It's just the idea. I mean, I've been doing software development here for 20 some years, and everyone's got their own environment set up, and different libraries need to be loaded, and you spend half a day just trying to get everything coordinated with a new engineer coming on, and Docker has just like completely revolutionized that, right? It feels like that's kind of what you're trying to do here. It's you don't want to download a Jupyter notebook that has all these other dependencies. It would be nice just to have an environment where you can just spin it up. So it seemed like it was a little bit, there was a corollary to it.
But I think you're right on target. That's exactly where we're going. Ultimately, we want to try to figure out how to work in a containerized environment. Cool. And I think you'll see that here in just a minute. So this is to the subject of open source tools. So what are some of the tools that are emerging specifically with respect to MLOps? And you think through the list of challenges. So first challenge is, how do you provision compute? Not just compute, but compute that is secure, that is scalable, that is reproducible, and do it easily, right? So you could go to pick your take your choice of cloud provider, and you could provision a VM of any given size for every user in your organization. If they put their code in Git, they might be able to collaborate, but maintaining environments and reproducing that in a production system isn't going to work. And once you get to data sets that exceed the size of the VM, now you have problems. And let's not even talk about the challenges of maintaining those platforms as people come into and out of the organization. It's just that ends up being very difficult to scale. So the approaches that many organizations are taking are to go down a distributed platform, down the path of a distributed platform. So what you need on the exploration and modeling side, you can use, so full disclosure, I lean toward Python. I think we said that right at the very beginning. And you can use all of your in-memory Python tools, but then how do you do distributed training, right? Because eventually you're going to deal with the data set that's too large, or you're going to deal with trying to train a model that takes 14, 18, 24, 46 hours. And that's when you need some distributed tools. Spark enables that. That's historically been used for that purpose. Dask is a little bit younger than Spark, but it's a pure Python library that effectively allows you to parallelize any Python library, any of the standard data science Python library stack. Provisioning compute. So there are a couple of open source projects that really drive this. Kubeflow was open sourced by Google a couple of years ago. It runs on top of Kubernetes. It comes with Jupyter notebooks enabled for users for exploratory analysis. Netflix open sourced Metaflow a few years after that. And that is their data science platform built internally. They don't use Kubernetes, they use their own system. It's called Titus, but it is a distributed environment. And then they have a customized version of Jupyter notebooks. So those are two open source projects. And then pretty much every cloud provider is offering some version of they're offering their own version of MLOps in some form or fashion. Experiment tracking and artifact logging. So if we want to deal with things like reproducibility, traceability, then we need some tools that let us do that. MLRun is a project that's geared at the Kubeflow platform. It's also offered by a software provider. MLflow is open sourced by Databricks. And they turned that over to the Linux Foundation, if I remember correctly. And then Metaflow has their own experiment tracking platform as well. Notice that I don't mention Databricks from a provisioning standpoint, and we might get to that. Well, I'll make sure I cover that. But for one thing, it's closed source. And then workflow scheduling. So Apache Airflow, that was mentioned earlier. It's interesting because Apache Airflow has actually, the challenge with Airflow is that it doesn't deal well with high velocity data. It's more of a slow running batch job. Prefect is, it's a newer version of Airflow. It's geared at data science workloads. Kubeflow also has, as part of their platform, Kubeflow pipelines, which allows the orchestration of data science workflows. And then Metaflow has one as well. So what we want to do is we want to take all of these things and we want to then leverage software engineering tools. So we want to be able to write unit tests. And this is, again, I'm knocking on Jupyter notebooks, but pretty difficult to write unit tests for anything that's in a notebook. It just doesn't, you can do some kludgy workarounds and try to make it functional, but boy, you just can't, if you need to write unit tests for Python, you just can't beat PyTest. And once you start getting into that framework, now you can leverage things like Git hooks and GitHub Actions to automate those processes, Azure pipelines, right? We're starting to get those, the best practices from software engineering in place. So if we were working in something like Kubeflow, what would a development life cycle look like for a data science team? From an infrastructure point of view, so we're in a container orchestration environment like Kubernetes, which means we have a distributed compute platform. Kubeflow comes with Jupyter built in. So we can provision Jupyter notebooks for users. We can give them the flexibility to create a Python environment like they would normally use, just like you see on your local environment. Provisioning of compute resources is scalable. So when we provision this Jupyter notebook, we can provision 200 gigs of memory and 12 cores, or we can scale it down. We can say you can get up to 16 gigs or 8 gigs, take your pick, right? But the beauty is, because we're in a distributed compute environment, if we need to call out to something, we can, right? If we need to connect to a Spark cluster or the Spark operator, if you're on Kubernetes, or a DAS cluster, we can do that. So they start their exploration, they do some prototyping, they're working in their notebook. Hopefully they're collaborating with their peers. We're working on top of Git, so we want to check our code in on a daily basis. Eventually, during this process, as they go through the exploration, the code that they write in their Jupyter notebook, they're going to start to refactor it into functions, and then they're going to call those functions from the notebook. So what we ask to do is that as that gets stable, let's factor that out of the notebook into a pure Python file. Why would we do that? Well, because now we can start to bring in software engineering best practices. We can, if we need to, we can lint our code. We should, right? We can write unit tests. But the other thing that we get is the ability to import that back into our notebook. So now this is an isolated function. Not only can we do all of our unit testing, our linting, but we can share these functions with other people. They become now immutable and idempotent. So we go through that process. We continue developing, we start doing model creation. Eventually we get to the point that we have a model, right? And we think, well, that's pretty stable, right? We like that. So now we can log it into a database. And we version control the data set that's used to train it. So now we have the ability to reproduce our work. Every model becomes unique, and it's completely seamless to the data scientist. So there's going to be a lot of iteration in this stage, and we may eventually. So we encourage people, start with in-memory data sets. It's faster, it's easier, right? Distributed compute adds complexities that if you don't have to deal with it, don't, right? But eventually you probably will. So now we introduce, right? They can go back and forth in this loop, and they can refactor these into Spark or Dask, right? Leverage these. And the great thing from my perspective about Dask is the same unit test you wrote for your pandas function, you can use for your Dask function. It's exactly the same. So we go through this process, right? Eventually we decide we're ready to automate. Well, these Python functions that we wrote now get embedded into MLRun objects for us, but the ultimate output is a YAML file. So we have a YAML file. So now we're treating infrastructure as code. We have a YAML file that embeds our Python file into the YAML. And now we can run it anywhere. We don't have to be in a notebook anymore. We can take that and we can put it into a container and create a notebook from that and start doing external integrations. So we can expose our model through an API, or we can call our pipeline through an API. And then we implement notification and monitoring. So in this way, we end up with an iterative process where the code that the data scientist writes eventually makes its way all the way out to production. And they have the opportunity to iterate on that.
I got a quick question, Greg, if you could
Yep.
go back. I mean, what is the mechanism? I guess I don't know about enough about Kubeflow, but I mean, how does that then feed back into Jupyter? Is there, because that's the beauty of it, is that it can get back in.
So Kubeflow is a collection of tools, of which Kubeflow Pipelines is one. So we use MLRun, which is an open source library that runs on top of Kubeflow, or Kubeflow Pipelines, but you can use Kubeflow Pipelines directly. There's a domain specific language that you use to build a Kubeflow pipeline object. And the output of that is a YAML file. So you effectively import you convert your Python module, the code that you wrote here, directly into for us, MLRun object, but a Kubeflow pipeline object.
Okay.
So the output of that is the YAML, and that YAML you tie to a Docker image, which replicates the environment that your development was done in.
Okay, sure. So then that can be brought back.
When we run this Kubeflow pipeline, every step in the pipeline is a Kubernetes pod. And that Kubernetes pod has everything that the data scientist had available to them. And it also has the code, the Python code, that's called and executed.
Gotcha. Okay, sure. And so then they can turn around and take that back into their own Jupyter notebook and sort of start the process all over again.
Yep.
Does this model, and maybe you deal with it with regards to just, I guess the beauty of machine learning, I guess, is basically learning from the predictions that you made over time, and then of course making the model better. Does this address that in any way, or maybe that's a future slide?
Yeah, it does. So there are two pieces to it, right? One is retraining the model. So once you have the feature engineering and the model training step, embedded in the Kubeflow pipeline. Now you can monitor that model in production, and you can also schedule retraining in production.
Sure. Okay. Sure.
You can also enable hot swapping. So you can look at the model you have running in production versus a newly trained candidate model and write logic as code to compare the performance of your current model against the new model and swap them out if necessary. You can, this is Nucleo, so this is effectively a serverless library that runs in Kubernetes. So if you expose your model through Nucleo, then you can have a canary function running alongside of it.
Nice.
So you can route two models against one another and compare their performance.
Gotcha. Yeah, cool. Yeah, I've done some work with TensorFlow and TensorFlow serving. There's a project a part of that, and that's kind of the same concept, but the tools aren't there to sort of, you know, to easily swap it out, and you got to write your own intelligence to be like, oh, we're looking at, you know, let's try version 3 of the model now. This is nice that it's kind of seems like it's built with that in mind. There's a lot of the building blocks are there for you. It's not like you got to write your own.
Yeah. So if you were to install, download and install Kubeflow, actually just install it directly onto, let's say, an AKS cluster or an EKS cluster, you would find some of the tools that I mentioned here are present, some are not. Some are optional to install. But you would certainly, so you would get Kubeflow, which would include Jupyter notebooks. You would get Kubeflow pipelines. You would get Argo for scheduling. So there are a lot of projects that are part or embedded in Kubeflow. One of those is also TensorFlow. PyTorch also runs on Kubeflow.
Neat.
So, I mean, this happens to be the environments that we use or the tools that we use, but you have many options.
Yeah, excellent. Thanks.
So I'm going to step back, right, and let's highlight a few things that maybe I said explicitly and a few things that I didn't say, but want to touch on. And the first part of this is taken out of a book called Building Machine Learning Powered Applications. But it very clearly articulates one of the things that we're trying to do. And that is take an iterative incremental approach. So one of the things that we see is this, and I've talked about this a few times, getting stuck in the loop of trying to build the best model, right? And it kind of looks like this. Like, I want to build a model. So I'm going to start with a wheel, and I'm going to take an axle. I'm going to put another wheel to it, and I'm going to have a car, and then I'm going to have a race car. And then I go to production. That's a very long running process. And if we want to adhere to design thinking, which is a customer-centric ethnographic approach, get something out quickly, right? That's not what we really want to do. Instead, we want to start with a simple model that delivers value, right? I mean, obviously you don't want something that's not value added at all, but increment your models, right, toward that race car when it makes sense. But get to value quickly. We don't want to spend so much time trying to build the best model that we forget that we're trying to service the customer with our product. A few other things, and these are kind of hot points, but you oftentimes see data scientists using CSV files. Terrible for so many reasons. Parquet is one of the newer file formats. It's binary. You'll typically see a Parquet file will be compressed to 1/10 the size of a CSV or a TSV file on disk. Moreover, Parquets offer you the opportunity to spill to disk when you're doing distributed compute. Leverage Parquet when you can. It's schematized. There's so many reasons to use it. I've said this a few times, version data and models together for traceability. This becomes more and more important, particularly if you're in fields or working in areas that have a lot of visibility, particularly to customers. We're seeing more and more people want you to explain why you got the result that you did. Why did I get the recommendation? And the other one is, and I mentioned this before, consider serialization early. If you're going to train a model that you need to run on a watch, you're probably not going to serialize it to a pickle file. It's just not going to happen, right? In some of the newer file formats, one of the more recent ones in the last few years it's come into play is Onyx. Onyx is backed pretty heavily by Microsoft, but it is an open source standard. And Onyx surfaces the Onyx runtime. So you can take a model that's trained in R, you could serialize it to Onyx and run it in Python as an example. You can also convert models from one runtime to another. So you could go from TensorFlow to PyTorch using the Onyx runtime as an interchange format. So I would strongly encourage looking at that when you think about how you're going to save your model. So we talked about the workflow from a development point of view. Let's think about it from a GitOps perspective. The use of source control is something that I think is, among data scientists, the familiarity with source control depends heavily on your background. So if you come at data science from a statistics background, rather than a software engineering background, then GitOps or the use of source control is something that's you're not going to be as familiar with. But ultimately, when we're building products, we need to get all the goodness that comes from software engineering best practices. So that means we have to figure out how to use source control. So what does a workflow look like? Well, we want our data scientists to create a Git repository, check their code into source control on day one. I mentioned Agile before, so we want our teams to work, or our data scientists to work as part of the product development process, which means you have other people, you're working in an Agile environment, you need a user story. What am I going to do, right? So by bringing data scientists into the product development process, we help assure that we time box the work, we declare what we're trying to evaluate for. Create a user story, create a topic branch. Link that topic branch to your user story and start performing your exploratory analysis, working on refining your hypothesis. Here's another one. Push your work to Git daily. We frequently hear data scientists say, well, yeah, I'll push it to Git when I get the finalized code. But when you're doing incremental releases, that becomes a real challenge, because the longer you wait, the further you diverge from what's in the main branch. And ultimately, you're going to have something that's going to be a headache to get back in. As we mentioned before, we're working in the notebook. Once we get functions that we're pretty comfortable with, refactor them out into pure Python files and import them into your notebook. And then we implement, for our case, through Azure pipelines, but GitHub Actions, write unit tests, right? Where they make sense, not just for the sake of writing them, but put them in and lint your code for human readability. Now we start talking about the actions of engineering, right? So from science to products. We can take these Python files, as we mentioned before, create ML run functions. And then once we have them into an ML run function, now we can run them out of the notebook. We can run them on the Kubernetes cluster as in whatever runtime we choose. We can run it in the Dask runtime. We can run it as a Spark operator. We can run it as an isolated pod. From here, we can create and test a Kubeflow pipeline in our local environment, and then create an experiment to run, and then issue a pull request, right? Have people review your code. This is not a bad thing. Code reviews are good. From here, we may have a dev branch, but ultimately we're gonna merge this back into main. And now we start to look just like software engineering with Python. So how would you release a new version of a Python package? Well, you would tag it and push it to PyPy. In our case, we have separate dev and prod accounts. So we want to create a service account. So we don't want our data scientists to be to have code running under their credentials. We want to get this under a service account. We want that because people leave, right? Things change. Have this run in a production grade environment and in dev, right? And then replicate that identically in prod when you're ready, right? So now we have a way that we can evaluate our code in something that exactly simulates production without risking what is actually servicing our customer until we know we're ready to do it. So a few final thoughts here. I shared this with actually my team not that long ago. At a high level, what we're talking about here is leveraging the Agile and the Scrum process. We want to facilitate communication with our stakeholders, other people in the team. Work hard to understand the requirements, document them, and link to your PBIs or your user stories to Git branches. We want to prototype and develop quickly. Another thing here important, what are the model metrics you're training to, and how do those align to the business objectives? We want to benchmark our models. So one of the things that we frequently see is we give a data scientist a problem, we give them a data set, and they jump to an XGBoost model. And you say, well, what was your benchmark? Right? In almost all cases, somebody somewhere has a heuristic that they're using for the decision-making process. And you should be able to beat that. That should be a benchmark. We look closely at package use in our platform. And finally, engineer and iterate. We want data scientists and ML engineers specifically to think carefully about performance. Don't use apply operations when you don't have to, vectorize, finally scale out to manage distributed compute. We started now looking for existing patterns in code reuse. There are a lot of common functions that data science teams use. We can pull those out and make them accessible to everyone on the team. So just a handful of things that we started thinking about to enable success. Finally, what are the benefits? Well, by moving into an agile environment, an agile work environment, we get much greater collaboration, not just among the data scientists, although that's true, and the ML engineers, but also with other functions, right? Because we have to remember we're building a product. We want to run the same code that we run from proof of concept into our dev environment and finally out to production. It improves reproducibility, and reduces time to product. We want to have common best practices to improve code maintainability. Again, by getting into a common work pattern and leveraging those across the team, now it gets easier for data scientists to move back and forth. They have much greater opportunity to develop, right, to learn other parts of the business. And the platform becomes more maintainable because people can move in and out and they know where to go to find the code and the data. And finally, we end up with a scalable solution process, right? We're not working on an isolated VM. We're working in a distributed compute platform that we can scale up on demand, right? And that supports the business. So that's what I had.
It's great, Greg. Very, very cool. Great. Thank you so much. Dan, you got a question?
I just wanted to mention it was a very good presentation. I love the overview. I would love your thought on the challenges of getting locked into a cloud provider's MLOps versus sticking with open source standard. We're on a company campaign to move everything over to one of the cloud providers, and I have grave concerns that we're going to be locked in for a long time if we use their stacks.
Yeah, so well, you notice that we use a Qflow based solution. So I lean, as you probably could tell, I lean heavily in the open source direction. And I think there's a lot more innovation that happens in the open source community. And you can still be on a single cloud platform and leverage open source tools, right? Or tools that are built on top of open source. In our case, I actually think there's kind of some interesting strategic decisions that Google made when they open sourced Kubernetes with that in mind. which is a whole other interesting discussion. Certainly there are a lot of cloud providers. Well, the cloud providers are all looking to build tools to lock you into their ecosystem. And they all have strong incentives to do that. But you can take an open source solution, you can deploy it into EKS, AKS, GKS. If you build your own open source tool, better, then you have to deal with security, right? Kind of all of the things that make an open source platform not production grade. But you can find vendors that can and will do that for you. So I think it's a balance. I think that we're going to see more and more cross-cloud solutions pop up because of the very concern that you've just articulated.
That's a good answer.
I guess, Greg, do you find a lot of people using private cloud, private solutions, or is it everyone sort of moving to more of a public distributed solution?
Well, there's certainly a lot of impetus in my experience toward public cloud type solutions because of the kind of the quote unquote infinite compute. I think one of the things that many organizations are becoming cognizant of is that it is infinite compute, but it's not free.
Right, there's a cost there to
right.
it, yeah.
Again, and I'm talking about the beauties of using a containerized platform, you can actually be split, right? You can be split between a cross and on-premise or cross public cloud on-premise solution, right? As long as you have the ability to run on Kubernetes. And a lot of organizations are doing that too, particularly where you need air gap solutions.
Cool. Sounds good. Yeah, if anybody else has got questions for Greg, I guess feel free to unmute yourself and shout them out. Totally open to that.
Yeah, I would say we're open to comments as well, so it's not just questions. So,
oh yeah, absolutely.
Yeah.
I just wanted to interject that the idea of having a model in a portable open format like Onyx is really a interesting idea, and especially since I'm working with a lot of hardware vendors, like an FPGA vendor that can do inference very, very quickly using an FPGA. And some of the people that have been in the AI Racing League know that we have these neural compute sticks that are really fast on inference, very low power inference for mobile cars. So I'd love to see more people doing portable models with Onyx and similar things so that inference can happen in many different environments.
Yeah. So Onyx is an interesting subject to me because there's a challenge I think that oftentimes gets overlooked, and that is, I mentioned in one of my slides that we're trying to encourage team members to use fitted transformers when building feature engineering pipelines. So the scenario that you see is I want to use XGBoost as my estimator, and I need to do one hot encoding, and I also want to do feature selection all in line. Trying to serialize that is a real problem because you can't directly pickle an XGBoost model. So you certainly can't pickle, let's say, an XGBoost model that's trained in a distributed format using Dask, while also leveraging a scikit-learn pipeline to do all of those feature engineering and feature selection steps as part of a reproducible process. So Onyx actually offers a solution to that problem. So it's pretty interesting. I'm just curious. I mean, are other folks on the call, are they working in this MLOps space? Is this a challenge that you guys see or work in at all?
In terms of the infrastructure and usage, right, to bring, I mean, currently we are also exploring the Kubeflow options. But as I said, we have a different platform where we are the current model build process is going. So it's something like if we have to make a switch over from that process to this, it will be little tedious. But one thing which I like is in your slide you showed, okay, still you go ahead and use the Jupyter notebook for your development, but once your development is done, put it into the Python node file, right? So I think there is one specific component, a Kale. It's a Kubeflow extension for Jupyter Notebook, which will help you to convert the Jupyter Notebook code into a Kubeflow pipeline enabled one. It's Kale. It's called Kale. Maybe that will be good thing actually. I mean, again, we are just thinking and started to think in that terms, haven't explored much.
Interesting. Yeah, one of the one of the challenges that we were facing when we started looking at Kubeflow was simply provisioning compute for our users. We were starting to scale our team up, and and not just internal resources, but also contractors and external resources. And we were provisioning VMs all over the place, and that became a real headache. Not just in terms of provisioning compute, but also managing the security. And then, right, is the VM large enough? And how large does it have to be? And and people not checking their code into source control. It just became a real headache. And
Yeah.
then when we went down the Kubeflow route, it's like, oh, you need a new notebook. Well, here you go. Right, here's 32 gigs of memory and 4 cores, and you're good to go.
Yeah, I mean, since you brought that point, right? The other challenge which we are currently facing is to use Kubeflow in GCP. We have to create the Kubernetes cluster, GKE, Google Kubernetes cluster, and the challenge again comes in place. The Kubernetes cluster needs to work within our VPC, our virtual network.
Yep.
So that is where another challenge that comes in. And the third one is when we run the code through the Kubeflow pipeline, right? In terms of the visualization of the results, I have seen some components which will help you to visualize the ROC graph or confusion metrics, but still it's evolving. If I want to see any intermediate results in a tabular format, I have to do a lot of coding over there. And other challenge I'm seeing is you have to write your, say for example, if specifically in terms of GCP, right? If your data is in GCP Hive, you need to create your data pro cluster using your Kubeflow and access your data. I mean, using the Kubeflow component, they have some component for accessing the data in your data pro, through data pro cluster. So again, searching for all those things and building it, it's getting a little trickier.
Yeah. So for a lot of the reasons that you articulated, we actually ended up going with a vendor um, on that front. We started looking at Kubeflow, and then we sit down and we took a real hard look. So it's no surprises for anybody that knows Ecolab. We work closely with Microsoft and Azure, and we sat down and we talked with our partners, and we said, this is what we're seeing. What are your all's thoughts on our observations? And they said, yeah. But they had just hired one of the guys that was one of the co-creators of Kubeflow from Google. And he was in our discussion, and he kind of pointed us in a few different directions, and it worked out really well because we have the same thing. We have to, our deployment is inside of our VPC, but it's in Azure.
Yeah, I definitely want to echo the fact that looking at these vendors, sometimes they do offer very compelling solutions. And especially when we had a small DevOps team that was building things to automate a lot of model deployment. But we realized that I think Microsoft has 400 full-time people working on MLOps now. It's hard to compete against those teams.
Yeah, we looked hard at Microsoft's MLOps offering. I think it suffers from my perspective, right, is one of the challenges with that implementation is it can get very convoluted. I think it works really well if you're dealing with one or two models at a time. But if you have a very large team and you want to deploy compute resources for every project, it started seeming heavy for us. But it's also matured a lot in the last year.
Yeah, absolutely. The last year has seen a lot of new features coming out.
Mm-hmm.
Seem to have more coming very soon too.
Yeah, and well, then you get into the philosophical question, right? Do you want to be tied to, I mean, it's an open source solution, but it's an open source solution that runs in one place.
Yep, that's the cloud for you.
Yep.
There's also a lot of innovation going on in parallel. We talked about using the one hot encoding a bit ago. And I think there's a lot of people within a lot of communities that are doing NLP modeling, building BERT. It's taking a huge amount of resources in a lot of these companies. And they don't seem to work very efficiently on the GPUs. And so we've been looking at a lot of other alternatives that are highly tuned for what we call the sparse matrix processing. And I think we're going to see a lot of innovation in the next year in companies that offer specialized hardware for doing specific types of models. Sparse models being image models are very dense. They work really well on GPUs. That's what GPUs were designed for, image processing. Yep. But man, they just do not seem to do well on natural image processing when the data is sparse.
Yeah. You know, we had an interesting example. This is more of an ML engineering type thing, but it's an interesting example of how you can alter the compute paradigm. We had a model that was created by data scientists. It was roughly 20 million rows of data. And they had one hot encoded a lot of the data. And it blew up from, I think it was 30 gigs in memory to something like 260 gigs in memory. And we took that data frame and we converted it into a SciPy sparse matrix and vectorized one of the operations. And we took it from something that took 8 hours to run and say 250 to 350 gigs of memory to something that ran in 8 minutes and consumed 100 megs in memory. So it's kind of a fun exercise.
The way you represent that knowledge is very critical, and one size fits all doesn't fit when you have specialized models.
Yeah, exactly.
Cool. Any other questions from the group here? Got a couple minutes left here for 8, but
I just
covered a lot of ground.
I just want to mention one other kind of slightly mind-bending idea that is been circulating a lot, and that's what's called in situ machine learning, where if you have enough horsepower in your database, you can actually train the model directly in the database. Now, that won't work with relational databases, obviously, but some of the newer graph databases and the newer graph hardware we'll see roughly 3 orders of magnitude increased compute power inside a knowledge graph. And that's going to change a lot of these MLOps because then you can continuously train as you get updated data and continuously get benchmarks. So it's going to be a very dynamic world in a couple of years.
Oh yeah, wow, that'll be pretty awesome.
Yeah, there's a nice, if you go just Google Intel Puma, P-I-U-M-A, there's some really good articles about how the hardware that is in fab right now is benchmarked at 3 orders of magnitude increase in it, but it's all sparse matrix type problems, right? And for image stuff, it's not going to really improve it. But for sparse matrix, hardware is going to change.
Wow, that's pretty cool. Yeah, I'll look that up. Thank you.
Yeah, I guess my thinking is all these new technologies coming in, at the end of the day, it feels like kind of I guess the overall feeling I get from your presentation, Greg, is just you're trying to orchestrate a bunch of different teams, from the product owners to the data scientists to the software engineers to the customer, bringing that all sort of full loop into this entire operational model. And it's just going to get more and more complex, I guess, when you keep throwing more and more different technologies into the mix. And it's just the whole operationalization of software development. It just needs, or just technology development, I guess, needs to be thought and planned and worked through and automated and just done to the best of you know, of our abilities. Because at the end of the day, whoever can do it the best is going to win. You know, really, if these models and these things are data scientists, or you showed it on your initial screen, if they don't get out to production, you could have the best thing in the entire world, but no one's going to see it.
Yeah, I think if you cut it all down to its core, in large part, we want to figure out, you know, how can you integrate, how can you kind of pull data scientists into the process of building a product, and connect them directly to the work that they're doing, directly to what, you know, goes to production, or at least as close as possible, right? And and not get caught in the loop of building a better model before you actually deliver value.
For sure.
It's hard. It's very challenging.